In this video, we are going to go off book and state some theorems involving limits that the textbook does not do in this section. And it's a little unfortunate in a sense that all of these theorems are going to have the same form. Let me get a easier to see marker. They're all going to have the form for some special function f. The limit as x approaches c of f of x equals f of c. And in a sense, having all of these rules together at once at this point of time is unfortunate and potentially confusing, because what we're trying to drive home right now is that that's not usually true. For example, if h of x is the heavy side function, 0 when x is negative, 1/2 when x is 0, 1 when x is positive, it is not true that the limit as x approaches 0 of h of x equals h of 0. The reality is that this limit does not exist. So now, giving a whole bunch of exceptions to that, when you compute the limit, it doesn't matter what f of c is, except for all these cases where it does risk being confusing, I think, but I think it's necessary. Because this textbook, I mean, we wouldn't use it if we didn't like it. It has virtues, but it does sometimes present material in very strange ways. For example, the limit as x approaches c of the sine of x equals the sine of c. This is an important result. You have to know it. And what the textbook author does in section 2.2, the textbook authors do an example. And that example is to show that this is true for one particular value of C. It's true for C equals 0. And then in a completely different section, I think section 2.5, in an exercise of all places, in exercise 64, they make the statement that actually this is true for every C. And why is this material being presented this way? It's so important, and it's being spread across multiple sections. Once in an exercise, a homework exercise of all things, then in an example that over half the class is probably just going to skip. Well, I've kvetched enough, but my point here is that we've got these results. They need to be presented. The textbook doesn't present them in any unified way. This is probably as good a time to do it as any. So, theorem. Let T of X be any of the 6 standard trig functions: sine, cosine, tangent, secant, cosecant, cotangent. Then the limit as x approaches C of a trig function can be gotten by simply evaluating the trig function at C. And we'll put in parentheses if C is in the domain. So this is always true for the sine and cosine, but the other 4 trig functions all have vertical asymptotes, points where they're not defined, and where you can't plug C in. Theorem. And all of these theorems are going to be the same. As I say, let I of X be any of the 6 inverse trig functions. Then the limit as x approaches C of I of X can be computed simply by sticking the limit into the function. Theorem. Let A be positive, and we'll look at the exponential function with A as its base. The limit as x approaches C of this exponential function can be found by plugging C into the exponential function. Finally, theorem. The limit as x approaches C of any logarithm can be computed simply by sticking C into the logarithm. And here we do need C to be positive, otherwise the logarithm isn't defined and the limit doesn't exist. But let's end with a statement, a reminder these theorems sort of are stated as such precisely because most functions do not have this property. So this is a special property that some standard functions have, but it's not a property that functions have in general. Maybe saying most functions don't have it is pushing things a little. Obviously, many of the standard functions we work with do, but the limits we're actually going to be working with in this class are again primarily of the following form, and limits of this form cannot be computed just by taking 0 and plugging it in. You get a division by 0 error if you do that. So I guess how I would summarize this, a lot of functions do behave nicely, but the expressions whose limits we care about are precisely the ones that do not behave nicely.